Okay, in this video we're going to look at chapter 4.4, Principle of Moments. Principle of Moments. I'm going to have a little introduction of the principle of moments, and we're going to look at a couple of examples, and actually we're also going to look at some fundamental problems. Not going to actually do any calculations, but we're going to just kind of apply these ideas of the principle of moments. Okay. What is the principle of moments? Let's come to the textbook here. If you recall in the previous sections, up till 4.3, if you have a look here, let's have a look at this figure here, 417. This is an excellent figure which illustrates the principle of moments. Up until now, what we've had, right? We've had a force and we've had a point of rotation. Okay? And so what do you normally do? In order to calculate the moment that this force causes about a point, we draw the line of action. Okay, this is obviously in two-dimensional space. Okay? We draw the line of action, and we determine the moment arm, which is the perpendicular distance from the point of rotation to the line of action of the force. Okay? So that's what we've done up until now. Okay, but sometimes it is not possible, the geometry and all the information that we have received, it is not possible to determine this moment arm directly. Okay, so what do we need to do, or what can we do? We break up this force into components. Okay, in this case it's XY components, but it could be any appropriate components or along any two axes. You break it up into its X and Y components in this case, and then you calculate the moment for each, the moment caused by each of those forces. So originally you would have had one force, one moment on, and you calculate the moment due to that single force. But because there may be many instances where it's quite difficult, if not impossible, to find this perpendicular distance, then what we need to do is we can break this force up into horizontal and vertical components, and then we calculate the moment due to that force, we calculate the moment due to that force, and we add them, and we get a resultant moment. Okay? So this is known as the principle of moments. Okay? And it's also called Variance Theorem. What does this theorem state? It says the moment of a force about a point. Okay? That's what we're used to. The moment of a force about a point is equal to the sum of the moments of the components of the force about the point. Alright? So the moment of a force about a point is equal to the sum, right? We're adding up the sum of the moments of the components. The sum of the moments of the components. So here, the moment of a force about a point is equal to the sum of the moments of the components. So if we add up the moment due to that component, and we add up the moment due to that component, we will get the same moment. It's equal to this moment, the moment due to this force about that point. Okay? And yeah, this over here, it says here MO, resultant moment, is equal to, let's just bring this closer. Resultant moment is equal to fx times y minus fy times x. Now where does that come from? Okay, so it says fx times y minus fy times x. So the resultant moment is fx, that's that force, okay, multiplied by this y component, right, because there's its moment arm, fx times its moment arm, right? Then it says minus Fy times x. There's Fy, there's the line of action, and there's the x, the moment arm. So the point is, there's the force, and you need to find the moment arm for this force. It's that value there, which is y. That's why we get Fy times x, Fx times y, and then we have Fy times, there's the force, there's the line of action, and there's the moment arm, which is F, which is x. So Fx times y minus Fy times x. Now, what is slightly confusing here is that, and I agree with you, you're saying why is that positive and why is that negative? I think in this case it's just a convention. They just chose clockwise to be positive, whereas normally what we would have is anti-clockwise or counterclockwise positive. Okay? So the point is that this force causes a clockwise moment, and what we learned before is that our convention was that the clockwise moment was negative, and then this force, if we draw the line of action down here and we multiply it by its moment arm, which is there, we will see that this force causes an anti-clockwise moment, which should give us a positive. So don't get confused here. I would still encourage you to still use the convention that we've been using up until now. Guys, what I want to say to you is this. This is not a formula to be memorized at all. This is a specific case for this diagram. If you memorize this formula and I find out, I will find you, and I will take your textbook and I will tear this page out of the textbook. Do not memorize any formula. Work from first principles, right? So you break up the force into its x and y, and then you add up the moments due to each force, whether it's going to cause a clockwise or an anti-clockwise moment. Okay, so I will find you. If you write out this formula without thinking, I will find you. I know who you are, okay? I know what you're thinking. Okay, so now, let's look at an example here. Here is an example. We have this rod or this beam, okay, and we have this force. Let's maybe try to bring it a bit closer. Okay, so we've got this rod, and we've got this force of 5 kilonewton. Okay, and it says determine the moment of the force about point O. Okay, very straightforward. So what we've done before is we extend the line of action, and we determine D, our moment arm, which is a line which is from the point of rotation to the line of action, but that is perpendicular to the line of action. Okay, very good. So is it possible to find it in this case? Yes. Just have a look at the way they do the calculation. You'll see in this case it is possible to find it. So then it's quite straightforward. It's the magnitude of F times that D, which then gives us this value of 14,5, and we can see that it is going clockwise. So they say the moment about O is 14,5 kilonewton clockwise. Okay? So very, very straightforward, but, say now it was not possible to directly determine D. Okay? Then what would you need to do? You would need to choose axes. Okay, they choose the y and the x and y. And what happens is we break up this force into x and y components. Now you've got a force Fx equal to 5 cos 45, and then you've got a Fy, which is 5 sine 45. So you've broken up that force into its two components, okay? Then what does Variance Theorem state? What does it state? The moment of a force about a point is equal to the sum of the moments of the components. The sum of the moments of the components. So we need to calculate the moment of each component and sum them up. And that will be equal to the moment of that force. Okay, I hope that's clear. Okay, so initially we had one force, and we could calculate the moment directly, but now we've got an fx and an fy because we've broken it up into x and y components. So just looking at this, what will this force give us? This will give us a clockwise moment, right? And this force will give us a clockwise moment, okay? So I just encourage you to don't just do the maths, but look at it and understand the concept, and so that you can come back later and you can say, but that my results agree with what I initially thought, okay? So now we've got fx. Now we need a moment arm. So we extend the line of action, and we have to find out what this perpendicular distance is. So the moment arm of this force, about point O, is this distance here. And that is equal to 3 sine 30, okay? Then the moment arm for this distance is this. Sorry, the moment arm for this force is that distance there, which is 3 cos 30, okay? So then, solution 2. All right, so here we see anti-clockwise positive. So what we've got here, we've got two clockwise moments. So immediately you can see, oh, okay, I've got a negative moment, and I've got another negative moment. Fx times dy minus fy times dx. So fx times this dy, and then we've got another moment, fy times dx. Okay? So let's come back here. And then we calculate that, and we get a final resultant of 14.5 kilonewton clockwise, minus 14.5. As you can see, it is exactly the same as the original answer when we used this diagram here. Okay? So I think that's good enough for this example. I'll just quickly go through the next example. Example 4.6. So what you see here, we have a bracket, and we have a force of 400 Newton, and we've got some lengths here, some distances, and an angle. Now, guys, what is your initial idea or your initial way to solve this? We extend the line of action here, and we try to find what is the perpendicular distance. Okay? Is it possible to do that here? No. As far as I can see, it's not possible to, if we extend this line, we don't have enough information to find that perpendicular distance. Okay? So what do? We carry out the principle of moments, which means we break this up into its x and y components, like this. Break it up into its x and y, and now we've got two forces, and now we need to calculate the moment due to this force and add it to the moment due to this force. All right? So if we've got this force, we have 400 Newton. Sine 30 will be the x component, and 400 Newton cos 30 will be the y component. Then I still need my moment arm. So if I extend this line of action of my fx, I can see that then will be my moment arm, which is 0.2. And if I extend this line of action there, I see that my moment arm is 0.4. Now, I just want to ask you, if we say that clockwise is positive, anti-clockwise is positive, then what types of moments do we have here? This force will cause a anti-clockwise moment. The Fx will cause an anti-clockwise moment. So the moment due to this force is positive. And then this force will cause a clockwise moment. So the moment due to this force is negative. So that's exactly what we had here. Okay? We have the 400 sine 30 times 0.2. That 400 sine 30 times the moment arm is going to be anti-clockwise, so it's positive. And then the other one will be negative. And we will then get this value here of minus 98.6, okay? Or 98.6 clockwise, Newton meter clockwise. Okay, so I hope that makes sense. We can't calculate the moment arm directly, so we need to break it up into its x and y components and then sum up the moments due to these forces. Okay, now what you notice here, remember guys, I just want to reiterate that we use the right-hand rule to determine our directions. So remember that if you use the right-hand rule, I can't really show my hand here, but there we go, like that. If you the right-hand rule, the curl of your fingers gives us the sense of rotation about an axis, okay, and your thumb is along that axis. So if we have a minus 98.6, and which means we've got a negative moment, which means we've got a clockwise moment, then what that means is that my fingers need to curl like that. Okay? You see that? They need to curl clockwise, which means my thumb goes into the page. And what does that mean when my thumb goes into the page? It means my thumb is going in the negative k direction. The negative k direction. So guys, remember, so in two-dimensional space, our direction is based on the curl of our fingers. But in two-dimensional space, when we are working with the scalar form, right, the scalar analysis, the direction or the sense of direction of the moment is based on the curl of our fingers, okay? Based on the curl of our fingers. Whereas in Cartesian vector form, which is generally three-dimensional space, the direction of the moment is based on our thumb, the direction of our thumb. Please, can you get that? I really hope that you would understand that. So this moment is causing it's a clockwise sense of rotation, which means if you use the right-hand rule, your fingers curl in a clockwise sense, clockwise direction, but your thumb goes into the page, and into the page is the minus k direction. Okay, so I hope that you get that. Okay. Similarly, if you go and do this and you do the vector analysis, right? We first need a position vector, right? We have our F. We need to convert our force into Cartesian vector form. How do we do that? Right? We just say 400 sine 30 in the I minus 400 cos 30 in the J. Right? These are the two components of your Cartesian vector, 400 sine 30 in the I minus 400 sine cos 30 in the J. That is your vector that is your force in Cartesian vector form. Then what did we learn before? If we carry out the cross product, the R, the moment arm in the cross product, is a position vector from the point O to any point along the line of action of F. So we have a point there. So if we calculate our position vector from O to that point there, we get 0.4i minus 0.2j. Right? How do we get that? We go 0.4 in the I, and we go minus 0.2 in the j, and we get that. And if we carry out the cross product like we did before, we will get minus 98.6, which is exactly the same as this here. Again, I remind you, what does this mean? It means that we are rotating about the z-axis. Our thumb is in the minus k direction, and our fingers curl in a clockwise rotation. Okay? So hopefully that's helpful. I just want us to quickly look at a few of these. Just have a look here. I just want to ask you, I'm not going to do any calculations. Can we directly calculate the moment arm from this problem? To me, it doesn't look possible to calculate. You need to extend this line and then somehow find this perpendicular distance. to the line of action. So what do you need to do? You need to break up this 100 into Fy and Fx. Fy, which is pointing down, Fx, which is pointing to the right, and you need to add up. You need to calculate those moments for those two forces and add them up. What about this one? Again, if you extend the line of action of this force, you need to find a moment arm which is perpendicular to that line of action. It doesn't look possible to me, so you need to break up this force into its x, y, and then determine the two moment arms and determine the moments due to those two forces. Okay, not going to comment on that one. What about this one? Again, I don't know if it's possible. Doesn't look very possible for me to determine my moment arm directly. If I extend this line of action like that, then I need to somehow find my moment arm there. Doesn't look very possible. I need to use the principle of moments. Okay, so I just wanted to give you a basic idea of all these things. Okay, guys, so hopefully this has helped. Email me or leave some comments in the comment section if you have any questions. Cheers, guys.